Hello. Now we're going to talk about finding any local extreme values or saddle points for a function. And this one may have more than one critical value. All right, so basically we're going to do the same thing we did in the video before this, but if we have two critical values, we're going to do that calculation using the discriminant twice. All right, so first things first, we need the partial with respect to x, which is going to give me 3x squared plus 3y plus 0. And we need that partial with respect to y, which gives me 3x plus 3y squared. Now, these are quadratic. We're going to set them equal to 0 and solve. So 3x squared plus 3y is equal to 0. 3x plus 3y squared is equal to 0. In order to solve this, I'm going to use substitution. So for this first equation, I'm going to isolate my y. So I've got negative 3x squared equals 3y, negative x squared equals y. So I can take that negative x squared and plug it into my other equation for that y value, which gives me 0 equals 3x plus 3 times negative x squared squared, which gives me 0 equals 3x plus 3x to the fourth. 0 equals 3x times 1 plus x cubed. Solving this, I'm going to get x equals 0 and x equals negative 1. So I have two x values, x equals 0 and x equals negative 1. I need to know what my y is in terms of x. So coming right back up to this formula, if I plug in 0, I will get a corresponding y equals 0. And if I plug in negative 1, I square it's positive, but then there's a negative, so I get y equals negative 1. So therefore, on this function, I have two critical points. 0, 0, and negative 1, negative 1. So now what we need to do is we need to look at the second partials and the discriminant and evaluate them at these two ordered pairs. Let me clean my screen up. So we can see our first partial derivatives here on the screen. So let me go ahead and find fxx. That is going to be 6x. And fxy, so taking this function and treating it as y, I'm going to get 3. Over here, fyy is going to give me 6y. So what I like to do here is make a table. So we'll list our two critical points, 0, 0, negative 1, negative 1. And then I come down on this side to kind of make this look a little nicer, like a table. I will list my second partials. So I've got fxx being 6x, fyy is 6y, and fxy, we have 3. So if I plug 0, 0 in here, I get out 0. If I plug 0, 0 into 6y, again I get 0. And plugging 0, 0 into 3, I can't. That is a constant. I have 3. All right. Then we look at negative 1, negative 1. I will get negative 6, negative 6, and 3. All right, we also need the discriminant for each of these. And the discriminant is found by fxx, fyy minus fxy squared. So this product, 0 times 0 minus 3 squared, That discriminant gives me -9. Over here, this product is 36. Again, minus 3 squared. 36 minus 9 is 27. So now we come to the analysis section. For the point 0, 0, since the discriminant is negative, -9 is less than 0, we know there is a saddle point at 0, 0. And for -1, -1, since 27 is positive or greater than 0, since 27 is greater than 0, that means it's either a max or a min. So we come up here, we look at second partial with respect to x twice, -6. So since that second partial is less than 0 or negative, we know that this represents a max at -1, -1. So closing this problem out, going back to our original function, fxy was x cubed plus 3xy plus y cubed. If I evaluate that at 0, 0, 0, 0, 0, 0, my z value, or my output here, would be 0. So 0, 0, 0, the origin is the saddle point. And we have a maximum at -1 plus 3 minus 1, which is +1. So f of -1, -1 is +1. So we have a max of z equals 1 at -1, -1. So I hope that helps you guys understand finding these maximum and minimum saddle points, relative extrema for multivariate functions a little bit better. In the next video, we're going to talk about absolute extreme values.